Well, let's pick up where we left off last time. So last time we talked about losses within a piping system. So we saw that take a number of forms. We could see that in energy losses. We could see that in pressure losses. You could see that in head losses. Head loss being divided by gravity. This loss term, to this point, we have really only considered what we call major loss. And that's the loss of energy along the piping system itself. Now, that's great if the majority of the piping system is going in a straight line. What you find, though, is if you look at an actual piping system, so here's a sprinkler system where you've got, let's see here, so we can draw, this is a large union. And this is a large union joining two pipes together. I've got up here a bend, right? I've got in here a contraction, if you will. So there's all these places where the flow changes within the conduit. That's a real piping system. You're always going to have different bends and elbows and things of that nature. Anytime the flow changes, there's going to be an additional energy loss that we're going to have to try to quantify. We call these minor losses. And this is normally in most piping systems, what we've seen to this point, this is what we call the major loss. Normally this is the larger component, but it doesn't have to be. If I've got a system with lots and lots of bends, elbows, contractions, expansions, lots and lots of unions, then every one of those connections, there's going to be an energy change associated with those connections because the flow is going to change at that point. And so what happens is there's an energy loss that is associated with it we can find, and it's possible that these minor losses can actually add up to a quantity larger than the major loss. It just depends on how complex our piping system is. How do we quantify those minor losses? Well, the minor loss associated with many of these situations can be, we can approximate that with a loss coefficient. And most of the time in a fluid mechanics textbook, you're going to be able to find within the chapter that talks about these quantities. And you're going to hear a pop here. I got to look and see how this book comes in. So you can see here, this is in our text. You can see you're going to have a KL, a minor loss, associated with different types, depending on their parameters, different types of situations. Now in our text, it gives us kind of an extensive table here. And then for ours on the next page, and you can see here there's minor loss coefficients for some common fittings, if you will, bends, elbows, things of that nature. And so, and then some down here for some valves as well, so some different kinds of valves. And then if you look throughout the text, a lot of times in text they'll have charts like this that will show you for different geometries, different situations. They might give you additional minor losses in addition to typically a large comprehensive table within the text, some different quantities there. So that's where we would go to find some of these minor loss quantities. That becomes this KL. So every time the flow changes, we can typically find a minor loss coefficient to attribute to that change, multiply by the kinetic energy, the average kinetic energy flowing through that fitting at that point, or that change, and that'll give us an approximation for the energy loss. And if we divide by gravity, we get the head loss. Or if we If you don't divide by gravity, you get the energy loss. If you multiply by density, you get the pressure loss associated with that minor change in the flow. So, what do we do with that? Well, if I've got an entire piping system, this is kind of the most generic way to do it. In a realistic system, you're going to have some segments at one diameter, therefore, so the diameter can change at different points within the flow. And if the diameter changes, the speed changes. And if the speed and the diameter changes, that means the Reynolds number changes, therefore the Darcy friction factor changes. So we write a generic expression here where we're summing for all these individual diameters. You're going to have a different speed and a different Darcy friction factor within all of those pipes. And then for every, so here we've got a J on this summation, so for every minor loss, take the speed, the average speed of the flow through that minor fitting, that change in flow, take that speed squared. If you want the head loss, divided by 2G, multiply by the minor loss coefficient for that change in flow, and that'll give you this sum plus this sum gives you the total loss for the entire piping system. Now, this is again a realistic scenario. Now, what I would normally put on, say, an exam would be, I probably wouldn't put a whole bunch of different diameters on the exam problem because those are timed, and the algebra gets pretty intensive there. Having to find a Darcy friction factor for this pipe section and then that pipe section. Normally what we'll do is we'll just stick with a single diameter throughout the entire piping system. So again, recall that if the m dot, which of course is equal to density area times speed, right? So if the m dot is constant, so this is 1, 1, and 1, and that's equal to rho 2 A2 V2. Well, if the density is the same at 1 and 2, and the diameter and therefore the area is the same at 1 and 2, then that means that the speed is going to be the same at 1 and 2. And that's what we're saying here, is if the diameter is the same, as long as the diameter and the density are both constant, if the diameter is constant, the area is constant. So if the diameter and density are both constant, the velocities have to be constant. And if that's the case, then this expression here simplifies to that one there, to where I don't have to do large summation on, I don't have to add up the major loss for every section of pipe at different diameters. I don't have to add up the minor loss with all these different speeds. It's just the same speed. I can just find the average speed based on the conservation of mass throughout the piping system. Right? And so let's do, what am I on here? I'm still on highlights. So let's, now what I might suggest to you is again just to highlight. This is what we call, might be better with my finger there. This is what we call the major loss, and this is what we call the minor loss. Now again, there's no guarantee that the minor loss is going to be smaller than the major loss. Most of the time it will be. Most of the time we're trying to pipe fluid a long distance, so a lot of times this length of pipe is going to be so large that this quantity ends up being larger than this one. However, again, if I've got a whole bunch of different fittings or a whole bunch of changes to the fluid flow, if I do anything other than flowing that fluid in a nice straight line, I'm going to have a minor loss. And if I have enough minor losses, I can have a situation where the minor is bigger than the major. Just kind of be aware of that. It's not uncommon that we can just ignore the minor loss, that it is much smaller than the major loss. Again, for a nice straight piping system where I'm moving fluid in a straight line from one location to another, this quantity may not even be important. Okay? But if you do have a lot of bends, fittings, elbows, you probably want to look into it. I'm going to turn my ink off to do that. There we go. Okay, so example problem. Where am I out of my time? I'm going to stop the video there because there's no way I'm going to get this example done in the next 4 minutes that I've got left on this video. So I'll pick up here with an example after this. So loud pop coming.